Welcome to our video module on statics. Today I'm going to cover a really neat concept that allows us to reduce pretty complicated machines and pretty complicated setups to much simpler, faster equations. And it involves looking at energy and work. Now for this first little session, I'm going to just do a quick bit of review. If any of these are giving you grief or you're scratching your head, go ahead and take some time to review it. So you remember at the beginning of the course, I did a little bit of an analogy as I was looking at a seesaw, and here I am enjoying the seesaw with my daughter, but we found that if I was too far out, I would just go all the way down, and that ended up leading into summing moments about a point and making sure it always equals 0. However, there's some other things going on here. We can sum the moments to 0. Let's draw this out. We set up our torques equal to 0. We put in our torque rotating clockwise, counterclockwise, and we see that the weight of the parent, is 180 pounds. Now this is all standard stuff. However, I'd like to look at it from a different perspective. Let's say that the seesaw has gone like this, in which case I want to look at what is the distance that we have gone through. What is the work that each of us has done? Now, as a reminder, work is simply force times distance. Force times the distance in which you have moved. So in my daughter's case, let's say she's gone up 1 foot. Well, her force is 60 pounds, and the distance for her is 1 foot. So her work is going to be, or the work done on her is going to be positive. She's going up. Now, in addition, the work that I've done should be equal and opposite, because we're not creating energy. We're not doing anything special. So her work and my work, they should sum to 0. Nothing's changed. So my work, here let's do work child, work parent, and in my case, my force times my distance, and that's simply going to be 180 pounds. But take a look at my distance. I'm 1/3 of the way out, which means not only is this horizontal distance, but also the vertical distance will be 1/3. So that will be 1 foot. So that brings us down to say 4 inches. Okay, 1/3 of the way. We multiply that together, and in both cases, we end up with 60 foot-pounds. This should come as no surprise to anybody. In this case, the work going in equals the work going out. We simply multiply the force times the distance something is gone. Fortunately, this can be used in all sorts of setups. So what I'd like to do today is I'd like to introduce the idea of virtual work. So what we have here is a basic scissor jack. You can imagine that W is, some car or something like that pushing down, and we'll say that that is equal to 1,000 pounds. And for right now, what's keeping this whole thing from just collapsing, is each one of these points is pivots. And at the bottom, at this point right here, that's attached to the ground. This point right here is rolling. So what wants to happen, what this scissor jack wants to do, if there were just the weight, it wants to go this way. The whole thing wants to flatten. It just wants to push this way. However, I'm applying a force. That force applied is holding this weight up. I want to know what's the relationship between my applied force and this weight. Well, what we need to do is we need to set up a relationship between work in and work out. All right? Now the work in is going to be my force applied. We know that I'm applying some force, and I'm applying it in some horizontal dx. I'm going to apply it, I'm going to move a couple atoms. I'm just going to move a small amount here, and when I do that, I'm going to have W, meaning this weight, move a couple small atoms in the vertical direction, dy. Okay? Now I need to figure out what is the relationship between movement in the vertical direction and movement in the horizontal direction. Because if I can figure that out, I can find out what my applied force is. Let's take a look at this and we know that as this angle changes, or we suspect that as this angle changes, the relationship's going to change. Let's figure out what this distance is first, right here. We'll use this as our starting point. Well, each one of these lengths is 6 inches, right? So I'm going to do cosine theta times 6 inches, and that'll get me halfway. And then I'm going to go the other way. I'm going to multiply it by 2. And that is going to tell me what this value is right here, x, what this full distance is. Okay. Now let's figure out what this distance y is. Well, I know that I'm going to take sine theta times 6 inches. All right. And that'll get me to here. And then if I do it again, that'll get me to here. And if I do it again, it'll get me to the top. So 3 times sine theta, 6, that's going to equal y. So this is great. However, remember what has to happen. We need to know how much a change in x compares with a change in y. Now you hear that and you know what we're going to do. We're going to take the derivative with respect to theta for both of these. So dx d theta here. Go ahead and write it out yourself. I'm going to write this down. Here's our equation for dx d theta. However, we need to find out dx compared to dy. We need to put those in terms of each other, which means let's isolate d theta and find an equation for dx and dy as functions of each other. Here I've isolated d theta, gotten these two equations, and what we'll do is we'll set these two equations equal to each other and see what relationship we find between dx and dy. So with just a small bit of algebra, we've ended up with an equation that says the change in x equals negative 2/3 tangent of theta. All right, so it is dependent on theta, dy. Now, does this make sense? Well, first let's substitute it into this equation right here and see what we see. So f of a. Now let's show what we're going to do. We're going to take this dx and we're going to substitute this whole thing in. And what we'll do is we'll end up with dy's on both sides. So we can simplify that by simply saying f of a times negative 2/3 tangent of theta equals the weight. Now, does this make sense? We expect that the force to be huge if theta equals 0. So if theta equals 0, you have this really, really squashed jack, and it's going to take an enormous amount of force to get this thing, to hold this thing up. Does that make sense? All right, well, if tangent theta is really close to, is 0, if theta is 0, tangent theta is really close to 0. This is a really small number, which means the force applied has to be huge in order for us to get 1,000 pounds on this side. Conversely, let's say we're really close to 90 degrees, which means that you have this really tall jack. And I wouldn't want to be underneath the car, but it does mean that you don't have to push too hard. You just push in a little, and you can really hold that thing up. Does that make sense? Well, here, tangent theta is going to be, if theta is approaching 90 degrees, tangent gets really high. So if this number gets really big, force of A gets really small. So this does bear with our intuition of what we would expect to see. And in fact, this is correct. Now, what I'd like to take a look at now is what have we done so far? First, we've used our idea of work to set up a relationship between input and output. And in this case, it's force times distance. Secondly, we used the geometry to set up a relationship between y and x. And really, y was our output. Sorry, y was our output. X is our input. So we're trying to find a relationship between two variables based on the geometry. The next thing that we did is we took the derivative. We took the derivative so we could see, we'll just say d by dx. We took the derivative to see how things change. And then finally, we substituted back into our original equation and found, used the idea of principle of virtual work to shortcut all those other things that we might have done, to shortcut all the other work we would have done if we had to figure out what was going on in every single member. So this allows us to shortcut what's going on in the internals of the machine. As long as we know what's on the input and what's on the output, we can proceed and we can find our solutions. Now that said, it doesn't always work like that. Sometimes there's friction. And if there's friction, what we say is the efficiency is simply the work out divided by the work in. So if for some reason you do have friction and you need to correct for it, simply use this equation. Efficiency is work out divided by work in. That said, I think you'll find that this tool of virtual work is very powerful in complex machine setups. Thank you, and I look forward to our next module.